Okay, so we're going to talk about one of the many different types of functions you're going to see in Algebra 2, which is polynomial functions. So you've technically seen polynomial functions before, specifically y equals mx plus b, which is slope-intercept form. You saw that back in Algebra 1. Slope-intercept form is technically a polynomial function. We just don't say that it's a polynomial function. So a polynomial function is in the form all of this craziness. It looks like a lot, but let me break up each of the pieces. A sub n minus 1, pretty much all of the numbers that are in front of a variable or that are the constants at the end, these are all coefficients. So specifically the ones in front of variables are coefficients. The one at the end is just a number, so this is just a constant. All of these are supposed to be real numbers. A sub n is not going to equal 0. So the leading coefficient in front of the highest exponent should not be equal to 0, and you won't see that. N is an integer, positive integer. So all of the exponents and the little n's that you have here, these are all positive integers. And I want you to understand and make a note of this. If you want to highlight it, you can. There should be no negative exponents here. There should be no negative exponents. When you have negative exponents, guys, it actually creates a different type of question or a different type of problem that we're actually going to talk about in the next couple of months. The next part is a sub n. A sub n is this guy in the very front of your equation. This is what's called a leading coefficient. You've seen a leading coefficient before. The leading coefficient is in front of your variable with the highest exponent. So it's in front of your variable with the highest exponent. Before we actually get into the Algebra 2 part of today, let's talk about what a degree is. Okay, so a degree, not from college, but a degree of a polynomial. This is when you have a monomial with the greatest exponent. So it's not just a monomial, it's specifically the variables in that monomial. So let me actually write this, variable and then in parentheses s. So it could be just one variable or multiple variables that are in a monomial, and you're just trying to find the greatest number. So for instance, for each of the polynomials here, 9, is that a variable? No, so that's why we put 0 for the degree. There's no variables to look at, so I can't find an exponent. X to the first power is the only variable, and the highest exponent you have on that variable is a 1. So that's why we said for the next question, your degree is 1. Next question underneath, we have x squared and x to the first power. The negative 5 at the end, you don't pay attention to. It's just a constant. We're just focusing on the variables. So for x squared, the 2 is the higher exponent. So that's why we wrote here our degree is 2. Some students will say, oh, Ms. Tapia, you have x to the first power. Yeah, I do, but I'm looking for the greatest exponent. So the greatest exponent here is a 2. Let's zoom in a bit. And then I'm going to skip over to the last one. How do you think they got a 5? Which ones? The first ones, the 2 and the 3. What's 2 plus 3? 5. That's how they got the 5. It specifically says a monomial with the greatest exponent. This is one big monomial. This is another monomial. This is another monomial. So the highest monomial is the first one, and 2 plus 3 will give you 5. So I want you guys, with the person next to you, if you want, try to do the questions over here on the far right. Find the degree for each of those. Just put the number in each of these places. I'll give you about 30 seconds. Yeah. What's the degree for the first one? 0. What about the second one?
1.
Not 5? No, you're only looking at the variable, guys. Even though the 5 is bigger, don't look at just the constants. You need to look at your variables. What about the next one, Mia?
2.
And the next one?
4.
And the last one?
5.
That's exactly it. All of these degrees, guys, are coming from the variable with the highest exponent. And especially since, I'm going to make a note up here, none of your exponents should be negative if it's going to be a polynomial function. None of your degrees should also be negative. So make sure all of these degrees are positive. All right, for the bottom portion, I might have to zoom out a little bit. This one says circle all of your polynomial functions, and then for each polynomial function, state the form and the degree. So we're going to label a few things. Okay, so first things first, I want to hear it from all of you guys. This first question here, does this follow the same form as this? The general form, does it follow the same form? Yes or no? Yeah, it does. Okay, so I'm going to circle number 1. That one looks good. What about question 2? Okay, it looks a little off. It has a parentheses, which is actually something we're going to see later on. If I wanted to distribute this x squared, what would it turn into? Plus what? This is a polynomial. This one, technically, even with it being kind of factored, because technically that's what form it's in, we can still write this as a polynomial. So I'm going to actually circle number 2. This one is technically a polynomial. They just factored. What about example 3? Look carefully at it. Yes or no? Is this a polynomial? Alex, why are you shaking your head no? What's wrong? I've been saying negative exponent. I even highlighted it at the top, guys. Since this negative exponent is here, this actually represents a rational function, which we're going to talk about in the next couple of months. So I'm going to put an x through that. Actually, let's put an x through the whole thing so you get excited that you don't have to do it. So I'm going to make a big X throughout the entire box. We're not going to do anything in that box. What about example 4? Is that a polynomial? Yeah, it looks like a polynomial. It has that same form like we saw on top. What about number 5? Yeah, this is a linear function technically, but it's in the form of a polynomial. I said that at the very beginning of class. And then the last part for question 6, is this a polynomial? Alex, you're glaring at me. What's wrong? What's giving you a question mark in your head? Well, it's not if it's a positive number. X is little. What does that mean? If X is little, what is it? Begins with an E. Help them out, guys. It's an exponent. If we have X as an exponent, we haven't seen that. If you look back at the items at the top, each of these X's are actual X's like we saw on the last question. None of those X's are in the exponent spot. What does it mean when you have X as an exponent? Specifically, you saw this back in Algebra 1. What type of function is this? Exponential. This is an exponential function, which you have seen back in Algebra 1. So this one isn't polynomial. So out of all the questions that we have, only numbers 3 and 6 are not polynomials. All the rest of them are. So for question number 1, we're going to actually answer the question. So the first part said, what form is this in? So this equation is in standard form. Standard form is pretty much descending order, guys. It starts with the highest exponent and it works its way down. Fair warning, on your tests and quizzes, I won't always put your questions in standard form, especially if I ask you to identify the degree, the LC, which is a leading coefficient, and your constant. So make sure you know the difference between them. What's the degree for this entire polynomial, Elizabeth? What's the degree for this entire polynomial? What number? 4. Next question. What's the leading coefficient for this, Elizabeth? What's the leading coefficient for number 1? Look at the number in front of the x to the 4th power. What's the leading coefficient? 1/2. Guys, and I want to make sure that you know this. Anytime you're identifying the leading coefficient, always refer back to the degree. The term that had the highest exponent, the number in front, will always be your leading coefficient every single time. That's what I specifically said. Yeah, so that's why I said that earlier. If I rearrange everything, your leading coefficient always has to be in front of your exponent with the highest, or excuse me, the variable with the highest exponent. So even if I rearrange it, this 1/2 would still be your leading coefficient because it's next to your highest exponent. And then last question, Elizabeth, what's your constant here? What's the number without a variable? -7. So we're just going to put that as our leading or our constant. For question 2, this is technically in factored form. This is in factored form. In factored form, guys, make sure that you understand, and I'm going to go through this when we actually start graphing, that you could actually find the degree from this. I know from distributing that my degree should be 3. Technically, when I actually give you guys your graphs, which we're going to do later, you would add this 2 with the parentheses right outside of it. There is technically a number. So it's either like 1, 2, 3, whatever. This number outside is a 1. So notice that I add this 2 plus this 1, and that's how I will also get your degree, which is 3. So we're going to go through this a lot more when we actually graph, but I want to expose you to, in case you have it in factored form, you can still find your degree, which is 2 plus 1, which is 3. The leading coefficient is just the number that's in front of your pretty much entire problem. So if it was a leading coefficient, it would be in front of the x squared here, or it would be in front of the x cubed, which is still a 1, positive 1. And then your constant. Is there a variable, or excuse me, a number without a variable here? No, so you just put 0. Do the same thing for 4 and 5. It should take you no more than 30 seconds. Andrea, for question 4, what form is this in? No. No, it's not factored. Standard form. It's literally highest exponent and then it counts down. Here's the highest exponent 4. It goes to 1, which is the next highest exponent. You're okay. And then the 9 is just a whole number. So this is in standard form. For question 4, Andrea, what's the degree? 4. What's the leading coefficient? Yep. And what's a constant? Perfect. For the last one, Andrea, what form is number 5 in? It is also standard. It's technically, let me clarify, let me make sure I can spell first. Technically, this is a linear function. It's technically linear, but as a polynomial, this is in standard form. The highest exponent is first, and then it counts down to the lowest exponent, which is none. What's the degree for this one, Andrea? Well, try it again. 1 is because this exponent here on x is a 1. What's the leading coefficient? Perfect. And what's the constant? Perfect. When you're ready, guys, flip it over to the next page. All of this stuff that I just did on this first page, this is just a review of Algebra 1. That's all it is. On the second page, we're going to have a little fun. Not really, but we're going to have some fun in my head. What I want you guys to do is I want you to see if you can graph just a very basic linear, quadratic, cubic, constant, quartic, quinctic. See if you can graph any of those functions. They give you about 30 seconds or so. I just want to see a nice sketch. It doesn't have to be perfect. If you want to bring out a ruler, you're more than welcome to. But I just want to see a sketch. What would these look like if you graphed them? Probably do this in pencil just in case you mess up. We can kind of fix it. Remember, guys, this doesn't have to be 100% perfect. I just want a little sketch of what each of these are. So I want to know first, show me with your arm, what does a constant function look like? Ooh, it's actually side to side. This is a constant function. The vertical one, guys, the one that's vertical, so if I drew it straight up and down, this is undefined. I don't necessarily say it's constant because if I ask you to write an equation for a constant function, it would just be, for instance, f of x equals c, and c is just some number. It's some value. So a constant equation is just side to side. And the other reason why, if you had a vertical line like this, so pretend like the ruler is my line, how would you write the equation for that? Uh-oh. Not y equals. X equals. It would be x equals some number. So that's also why if I was asking for a constant function, it needs to usually have y for f of x. All right, linear, show me with your arm. What did you draw out? Something that's slanted? That works. So I'm going to draw something with a positive looking slope like this. And f of x would equal x to the first power. You can put y equals mx plus b, but just for this regular line, we're just going to do x to the first power. So I'm mainly looking at your exponents here. All right, for the next part, you have quadratic. What does a quadratic function look like? Show me with your arms. We literally just did this. Yes, it's a parabola. This either opens up or opens down. We're just going to graph the positive ones here. So f of x is going to equal x squared because that exponent needs to be a 2. For the cubic parent function, cubic, what does that look like? It's always fun seeing y'all try to make those with your arms. Let's like that. So our parent function for cubic functions are x cubed. Quartic and quinctic, technically we could go all the way up to like an exponent of 100. We're not doing that in high school algebra 2. There's no way. So for quartic and quinctic, I just want you to get an idea of what the graph looks like before we actually go through it. So a quartic function, what do you think quart means? What kind of exponent? 4. So it's going to be f of x is raised to the, or x is going to be raised to the 4th power. This graph, look at what I'm drawing first before you start looking at me crazy. It's going to follow a similar shape to quadratic functions. It's just going to have a little bit of gunk in the middle of it. That's what makes it a polynomial. So look at what I'm graphing first, and then I'll let you graph something. So it's going to look something like this. The part in the middle will vary, but it's going to probably look something like this. I usually tell my students it has a kind of a W shape. Both of the ends of the graph are still going to go in the same direction as a quadratic function, but the middle of this is going to be kind of yucky. It's going to have some little curves and twists in there. For a kinctic graph, what do you think the exponent is going to be for that? 5. So for the parent function for a kinctic, it would be x to the 5th power. Just like we saw the quartic function kind of mirrored a quadratic, same thing for cubic. The issue is it's still going to have, for a kinctic function, it's going to have some gunk and some craziness in the middle. So let me show you guys what it'll look like. It'll still have the same shape as a cubic function. It's just going to look something like this, where you're going to have some loops and some twirls kind of in the middle of it. This is just a very basic type graph. If yours doesn't look exactly like mine, you're okay. I just want you to keep in mind it's going to have the same shape as a cubic function, so it's still going to have the down and the up like the cubic function. It's just not going to be as nice and crisp in the middle. Whenever you're done and you're ready to move on, let's look at the next page. So of course, I could be one of those teachers who makes you start graphing day one, but I like to give you guys some background knowledge first, so that way you guys feel prepared when you come into class next time and we actually graph. So I'm going to go through some terms which are going to be beneficial with helping you graph next class, so you don't come in completely confused. First term is end behavior. So the end behavior, and I'm going to kind of flip back to your last page, the end behavior literally says as you graph to the left and right of your x-axis, what's happening in the middle. So first thing I'm going to ask you guys at the very top, if you have a marker of some sort, get it out, and I want you to highlight this box. Just outline it. You guys know this. I don't say it very often, but for this, I need you to memorize. I need you to memorize this table. And I'm going to try to help you guys with how you can memorize it to make it easier for you. So what this does is it tells you when you have an even degree or odd degree function with a positive or negative leading coefficient, what's going to happen to the ends of your graph. So let's focus in this first box. When you have an even degree with a positive leading coefficient, let's look back at the parent function notes that we just had. When you have an even degree, nod or shake, this is even degree, right? What's the leading coefficient for x squared? Just a 1, positive 1. Since your degree is even and your leading coefficient is a positive 1, what happens to the ends of your graph? Where do they both go? Up. So for every even degree with a positive leading coefficient, both ends of your graph go up. And if you're like, Ms. Tapia, that's not true. Okay, let's prove it with quartic. Quartic is an even degree, positive leading coefficient of a positive 1. Both of the ends go up. That's going to be true for every function that has an even degree and a positive leading coefficient. Both ends go up. Left side goes up, right side goes up. What do you think is going to happen if you have a negative leading coefficient? They're both going to open down. So it's going to go down to the left and down to the right. Okay, let's talk about when you have an odd degree with a positive leading coefficient. Let's look back at our notes. The ones on the right-hand side, these are all odd degrees, and they all have a leading coefficient of a positive 1. What happens at the far ends of that graph? What happens on the left? It goes down, so the left side goes down first, and then what happens to the right? Goes up. And that's the same for every single one of these odd degrees with a positive leading coefficient. It's going to go down first, then up. So down, then up. Negative, guys, is just going to be flipped. This is going to go up first, then down. This table is the most important thing on your tests, quizzes, homeworks, whatever you're doing. I would write this table out first to get in the habit of figuring out what your end behavior is going to look like. All right, so I'm going to look at letter A with you guys, and you guys in a second will do letter B. It says determine the sign of your leading coefficient, determine the end behaviors, and whether your graph will be an even or odd degree. Okay, first of all, if we look at the graph, the left side of this graph is going down. The right side of this graph is also going down. Emma, if that's true, what does that mean for your leading coefficient, which I'm labeling as LC? It's going to be a negative. And what does that mean about your degree? It's going to be an even degree. So that's one part. Here's the last part. The last part was asking you about the end behavior. So I'm going to label this out as your end behavior. On a lot of our notes that we did several months ago actually, we would see x approaches infinity, f of x approaches something. X approaches negative infinity, f of x approaches something else. We did this for all of the types of problems we saw. Cubic, absolute value, quadratic. We did this for almost every type of function. So Emma, tell me, as x approaches positive infinity, so as the function goes over here to the right-hand side, what happens to this curve? Where does it go? Perfect. And what about as x approaches negative infinity over here to the left? Where's this function going? Perfect. That's all you're doing. So on your tests and quizzes, guys, if I ask you to identify your end behavior, this is what I want. Do letter B. You have a brain. You have somebody next to you. If you need to use them, use them. But I want you guys to try to figure out all of the items that I just boxed for question B. Go ahead and do it. All right, Omar, let's see what we got. I know that the graph is down up. I know that for sure. Looking at your chart at the top, Omar, what happens to your leading coefficient if your ends are down up? Your leading coefficient is going to be positive. I'm just going to put a big plus sign. What about the degree? It's going to be odd. Okay, that's the first part. Looking at your graph, it might be helpful for you to look at your graph for this next part. Omar, as x approaches positive infinity, where's f of x approaching? Positive infinity. As x approaches positive infinity over here to the right, this graph is going to continue to go up, which is towards positive infinity. And then what about as x approaches negative infinity? F of x also approaches negative infinity. So this graph, as the x's go to the left, the graph is going to continue to go down the y-axis, which means it's going to negative infinity. Let me be clear, guys, and I want you to pay very close attention to this. On your tests and quizzes, if I ask you for the end behavior and you see a multiple choice question that looks like this, or on a free response and it gives you your end behavior, make sure you always look at your leading coefficient and your degree. So if it's multiple choice question, for instance, and I give you your leading coefficient and your degree, I don't give you the graph and I don't give you this down up, and I ask you to identify the end behavior, I would suggest graphing this out first and then using that to identify your end behavior. I don't want you guys trying to commit all of these infinities to memory because you're going to mess them up. So if you see a question like this and it asks you for the end behavior, figure out from the leading coefficient and the degree what's going to happen to the graph. Graph that out. Once you graph it out, then you'll be able to identify your end behavior. Make your life simple. Don't overthink it. Give me some nods or shakes. Does that make sense with what I just said? I don't want you trying to commit infinities to memory. All right, next part. So end behavior talks about literally what happens at the far ends of your graph. Let's talk about a linear factor. Linear factors says a linear factor of a polynomial reveals its zeros. Maria, what's another word for zero? Say it again. Roots. What's another word for roots? Your x-intercepts. So for this, you're going to talk about really just your x-intercepts. So linear factors, guys, is a fancy way of asking for your x-intercepts or roots. So for this equation here, for the first one, I'm not going to do the second one with you. But for this first one, if I asked you to find the roots, Maria, what would you do besides panic? Factor, but what does it need to equal? 0. So we're going to make this equation equal to 0. And then you're absolutely right. We're going to have to factor. So Maria, help me factor this. What should I factor out first? An x, just an x to the first power, which is going to leave this in parentheses. Now what? What should I do now? All right, we're going to create the x chart for the item in the middle, so in that parentheses. I need to find two numbers that multiply to negative 15, but add up to negative 2. What two numbers can I use, Maria? 5 and who? Negative 5 and 3. There we go. When you multiply those, you'll get negative 15. When you add them, you'll get negative 2. So I'm going to rewrite this as x times, I want all of you guys to look up for just a second. In this parentheses, this x squared, what's the leading coefficient? What kind of 1? Positive. The only time, and I know somebody's not paying attention, the only time you can just write both of your binomials is if this number in front of x squared is a, what did you guys say it was? Positive 1. That's the only time you could just immediately write both of these binomials. If this number was a 2, a negative 1, a 3, a 4, a 5, I can keep going through all the numbers. If it's anything other than a positive 1, you have to factor by grouping. You have to. So I'm going to take this x minus 5, x plus 3, and we're going to set that equal to 0. Brooks, if I was to set this equal to 0, what does that mean for this? What would I have to do to each of those? Okay, so how would I set that up, though? Because I like to have it set up. If I asked you to solve this for each of it, I don't just want x equals the number. How would I set it up? Tristan, help him out. And then x equals 0. Phew, thought you were going to forget this x. Guys, this x in the front is a freebie answer. That x is a 0. That's all. So, Tristan, how would I solve the x minus 5 equals 0? Add 5. So, x would equal 5. That's one of your x-intercepts. Here's another one, x equals 0. And how would I get the 3 by its, or the x plus 3 by itself? There we go. So, x equals negative 3. Each of these guys are your linear factors. Your linear factors are 0, negative 3, and 5. Those are your linear factors. It's just an x-intercept. For question 2, right underneath this, as some of you guys are finishing that up, it's already factored. So linear factors literally mean just set it equal to 0 and solve. I don't know why I asked you guys to write this in standard form. So just cross that out if it's on your paper. If it's on your paper, guys, just cross that out, because after you solve, you can't really put it in standard form. Once you're done, guys, flip it over to the next page. This is the last thing we're going to get to today. The last thing we're going to talk about is multiplicity. Okay, so let me kind of refresh your memory as to what we've done. We've already talked about degree. That tells you the monomial with the highest exponent. We've talked about all the different types of parent functions, at least the ones that are relevant to Algebra 2. We talked about your end behavior. This chart, guys, you are going to need to commit to memory. So I would suggest writing it on every homework, every test, every quiz for this unit. And then your linear factors, guys, it's almost the exact same thing as your x-intercepts. They're pretty much the same. It's just your zeros. The last thing that I'm going to talk to you guys about is your multiplicity. Multiplicity sounds disgusting, but it actually is very closely related to your linear factors. So the multiplicity of a 0 is equal to the number of times its corresponding linear factor occurs. So on this graph that I have here, I'm actually going to use that to kind of hammer in what a multiplicity is. So I'm going to write out some values for each of these x-intercepts. How many x-intercepts are on this graph, guys? There's 5 of them. I'm going to give just some random numbers to each of them. Here's negative 4, negative 1. I like 2. 4 is even, and it's my favorite number. We'll use that. And this number down here will make 8. So we have 5 x-intercepts. They are x equals negative 4, x equals negative 1, 2, 4, and 8. I'm just giving it some numbers. What a multiplicity does is it has you focus in just with laser vision into each of these x-intercepts. It's asking you what's happening at each of those x-intercepts. Well, it kind of already describes it here. It says that these two it crosses, this one it touches, and this one it also crosses. Let me ask you this, though. Are these two crossings here, for instance, for negative 4 and positive 8, is it the same type of cross? No, the shape looks a little different. This one kind of swiggles through. This one just crosses. What these are they're actually different types of functions that are crossing through it. If I was to zoom in, and I'm actually going to do this, if I was to zoom in just on negative 4, and I was to have you ignore everything that's going on around negative 4, you see how it just crosses through like a line? What type of function is that? We saw that on the very first page, if it crosses through just like a line. Linear. This is a linear type of function. When it's a linear function like this, it literally crosses through just like a regular line. Down here underneath x equals 4, I'm going to leave some space for a reason. I'm going to put your multiplicity is equal to 1. It crosses through your graph like a linear function. It's just like a line. look at -1. How is that line crossing through? It's just like a linear function. It's literally just crossing through, just like a regular line. So I'm going to highlight that to show this part that I'm highlighting in yellow is crossing through just like a regular line, linear function. And I put multiplicity is equal to 1. I'm going to zoom out just a bit. What about x equals 2? If you were to ignore the rest of this graph and just focus in on 2, what type of function does that look like? Let's look back on the second page. What type of function does that look like? It kind of looks like a quadratic function. It's really just bouncing off. For quartic, it's not having this kind of weird jerking and swirling that it's doing in the middle. It just literally touches and then it goes away. So for this graph down here, for the touch that it has, this little bump is representing a quadratic function. So underneath it, I'm going to put your multiplicity is 2. For x equals 4, and that's for this little curve. For x equals 4, what type of function do you think crosses through there? What type of function does it look like? Linear. And what about x equals 8? That is definitely not linear. What does that kind of look like? Cubic. That one looks cubic because it has that shape that it kind of curves down. So this is actually for your multiplicity for 8. Your multiplicity is going to equal 3. It's going to cross through like a cubic function. What that multiplicity does is it tells me and you, when you graph these later, what type of shape to actually draw through each of those x-intercepts. So next class period, we're actually going to graph these and use these multiplicities to help us. In the meantime, though, we're just going to solve the equations that we have here and describe what is the multiplicity and what will it do to our graph. So let's go ahead and look at the first example. I'm going to do the first one. You're going to do the second one. In this first example, if I asked you to find the zeros, which are the same thing as your linear factors, what would you need to do? Set it equal to 0. And we're going to have to solve. The great thing is, this is already factored, so I don't have to worry too much about this. I'm going to take the x plus 7 squared, set that equal to 0. I'm going to set the 2x plus 1 equal to 0. And the x minus 4 cubed equal to 0. Okay, if I was to solve this, don't worry about the squared. That squared is there for a reason. I'm going to do x plus 7 equals 0. Just take the information in your parentheses and set it equal to 0. I'm going to subtract 7 on each side. So x is going to equal -7. What this 2 represents, guys, is your multiplicity. This 2 represents your multiplicity. When your multiplicity is 2, look back at your graph. What happens when it's a multiplicity of 2? What does the graph do? It touches. It literally bounces off of the x-axis or touches. So underneath it, I like bouncing. So we're going to put bounce. This is going to bounce off of the x-axis. Let me make another note here, and I kind of talked about this at the top. It says look out for double roots. Let me talk about double roots for a second. You see how that squared is there? What does that squared mean by definition? What does that squared mean? 2 of the exact same thing. So you technically have x plus 7 equal to 0. That's technically what you have. Don't write that out, by the way. Don't write it out. The reason why, if I was to solve both of these answers, what would you get? -7. So that's represented as a double root. We don't graph it as a double root. We just graph it with this little bounce that we see here, that little touch. So whenever you see a double root, guys, it's technically 2 x-intercepts at the exact same place. I just have you graph it one time. So whenever you see an answer that has a multiplicity of 2 or even 3, it represents more than one x-intercept that you technically are, quote, graphing. That's all it's saying. So let's finish this up with the last couple of things. 2x plus 1. Okay, we'll take the 2x plus 1, set that equal to 0. I'm going to subtract 1 on each side. And I'll divide both sides by 2. So x will equal -1/2. Okay, well, I took the multiplicity from the little number outside of this parentheses. Desiree, what's the number outside of this parentheses? I can't see it. It's a 1. That means your multiplicity for this question is also 1. Look back at the graph. Desiree, when you have a multiplicity of 1, what does it do? It crosses, like what type of function? Like a linear function. So this is going to cross like a linear function. I'm going to box that. And then for this last one, we're going to take that x minus 4, set it equal to 0. I'm going to add 4 to each side. X is going to equal 4. Michelle, what is this, or the multiplicity for this binomial? 3. What does that mean if I was to graph that out? What would it look like? It would look like a cubic function. So this part over here, how it kind of curved through that x-intercept, that's how it would look. So this would cross like a cubic function. Technically, and Emma kind of mentioned this earlier, when you're solving this, guys, and I think Desiree as well, whenever you're talking about this, the x minus 4, you would technically need to solve it 3 times. But instead of having you solve it 3 times, we just have you solve it once and create this little cubic curve. That's all we're having you do. So technically, this is one of the special ones. It's a triple root, but we don't really tell you that it's a triple root. It just technically will cross the x-axis 3 times at the exact same place, which is why we just draw the cubic function through it. So all of these items can literally be placed in this little chart, but just for the purposes of time, I'm not going to put it in this chart. Your zeros are the x equals, the multiplicities are labeled, and the effect is at the very bottom. So what I want you guys to do, I'm going to give you about 4 minutes. I want you to solve this equation. Yes, you're going to have to factor, have fun. And then I want you to label the x-intercepts, or the 0, the multiplicity, and the effect. What's happening to the graph? This question, the first thing you should have done was set the equation equal to 0 and factored out your GCF. That's the first thing you should have done. When you factored this out, you should have had x squared. What was the first binomial? X plus who? X plus 2. And then what's the other one? X minus 4. Be careful with that, guys. So you had 2 things you should have done. X squared equals 0. X plus 2 equals 0. And x minus 4 equals 0. First thing you should have done was x equals 0. Whoops, shouldn't have boxed that completely. That's one of your x-intercepts. What's the multiplicity on this? Which means it's going to do what? It's going to touch or bounce off of the x-axis. You're okay. If you write touch or bounce, it's okay. For the next one, you have x plus 2 equals 0. We're just going to solve, so x should equal negative 2. What does that mean for your multiplicity? It's going to be 1. And what does that do if it's 1? It crosses like a linear function. It's just going to literally cross through it. And then the last one, you have x minus 4 equals 0. What's x going to equal? 4. And what's your multiplicity? And how does it cross? It crosses like a linear function. This is just the first part, guys. So all we're going to do next class period is we're just going to take all of these pieces and combine it so that way we can actually graph these functions.